Okay, let's look at another related rates example, similar to a problem where someone is walking away from a light source, and the question might ask, how fast is the length of the shadow changing for that person? Very similar setup to this problem. You can read the problem on your screen right there. In this question, they're asking how fast is the tip of the shadow moving, not how fast is the length of the shadow changing. So let's talk about how to set this one up instead. The first thing we see is a street light is mounted at the top of a 12-foot tall pole. So I'll sort of indicate the pole here, 12 feet tall, and we have a light source at the top, okay? And then there's a man 6 feet tall walking away from the pole with a speed of 5 feet per second along a straight flat path. So let's establish the straight flat path. Maybe it looks like this. And we've got a 6 foot man tall walking away. So 6 foot tall man walking away. So let's draw him in here somewhere walking away from the pole. And we know that that height is going to remain 6 feet tall no matter how far he goes. We also know the height of the pole will be 12 feet tall no matter what. Now, the question is, how fast is the tip of the man's shadow moving when he's 30 feet from the pole? So the shadow that's going to be cast by the light source is going to emanate from the top of the light pole down across the man's head to the ground. And so the tip of his shadow is right there because his shadow is from his feet out, right? The question is interested in how fast is this point, this highlighted point, the tip of his shadow moving. So where most people mess up here is they like to call this distance in front of the man, or the length of his shadow, they like to call that x. So if we call that x and we find dx dt, what we have is a rate of change as to how fast the length of the shadow is changing. That's not what this question's asking. This question asks, let me see if I can turn my eraser on here. There we go. This question asks how fast is the tip of a shadow moving? So we have to measure from the tip of the shadow to some stationary object to measure how fast it's moving. And so we have to use a variable to represent the distance all the way back to the stationary light pole, because the man is moving. So this distance we talked about here before is changing all the time, right? That the starting point and the end point are both moving on that distance. So when we want to know how fast the tip of the shadow is moving, we have to go from a stationary origin to the tip of the shadow. So we're going to call that x, all right? And our goal here is going to be to figure out dx dt, how fast x is changing. How fast is this point moving away from a stationary object? Now, don't misunderstand me. I'm not saying x is the length of the shadow. X is the distance from the tip of the shadow to a stationary source. So that's how we measure how fast something moves. Okay? Now, what else do we have? We haven't used the fact that the man's moving at 5 feet per second. Well, the man's walking away from the light pole. So we need to incorporate a variable so that its rate of change is 5 feet per second. So what we'll do here is we'll measure again from a stationary source, the light pole, to the man, and we'll call that distance y. Because we know that dy dt, right, that distance, that y value is changing at 5 feet per second. So we know that dy dt is 5. And now we can see that in our drawing, the rest of this path is unnecessary. We only needed the triangular portion here. Now we can try to set up some equation, differentiate it, and solve for dx dt. All right, so we have what we call similar triangles here. We've got this bigger outer triangle, and inside that we have this smaller similar triangle. So we can set up an equation using proportions for those triangles. So what we have is, if I look at the big triangle, I can take the bottom side x over the vertical side 12 of the big triangle. That proportion should be equal to, or that ratio should be equal to the similar ratio for the smaller triangle, which is, so if we did x over 12 on the big triangle, we would do this side over 6 on the small triangle. Okay, So the question is, what is this horizontal green side? Well, if the big distance is x on the bottom and this piece is y over here, then the short side here has to be x minus y. The total distance minus y would be x minus y. So the other ratio would be x minus y, the horizontal side of the small triangle, to the vertical side of the small triangle, 6. And that's our relationship. That's our equation relating the x and y values in this picture. So let's rewrite that because we know we're going to differentiate it. So let's rewrite it to call it 1/12 x equals 1/6 x minus 1/6 y. All right. Now it's going to be easy to differentiate. And so we're talking about rates of change. We have to differentiate both sides with respect to t. So I'm taking the derivative with respect to t of both sides. So we've got d dt of 1/12 x equals d dt of 1/6 x minus 1/6 y. And remember, x and y are both values that are changing with respect to time. They're both functions of time. So when I differentiate 1/12 x with respect to t, I get 1/12 times dx dt. And on the right side, I get 1/6 times dx dt minus 1/6 times dy dt. Now what I can do is I can substitute in anything I need, or anything that's given, and then solve for the unknown dx dt. So what we're going to do is everything with the dx dt I'm going to get on the same side. So let's subtract 1/12 dx dt. So I've got 1/6 dx dt minus 1/12 dx dt. So those are my dx dt's on the right. Now let's get my dy dt over here on the left. So I'll add it, making it positive 1/6 dy dt. And I do know that dy dt is 5, so I'll go ahead and plug that in as a matter of fact. So on the left side I get 1/6 times 5. And on the right side I have two terms with dx dt. I need to combine those. So if I've got 1/6 dx dt minus 1/12 dx dt, I could factor out the dx dt, or I could just subtract 1/6 minus 1/12, which gives me 1/12 dx dt. So whether you factor out the dx dt or you subtract, you get the same thing. And so now we can finish solving for dx dt. Multiply both sides by 12. So dx dt will be 5/6. 1/6 times 5 is 5/6. But then I multiply by 12. And the 12 and the 6 both cancel, giving me a 2. So dx dt ends up being 10. A nice answer. Dx dt means that this x value, the distance measured from our stationary point to the tip of the shadow, that distance is changing at 10 feet per second. So the shadow's tip is moving at 10 feet per second. Notice we didn't even need the 30 feet from the pole portion. That means that the speed of the tip of the shadow is not dependent on the location of the tip of the shadow from the pole. It's a constant 10 feet per second as long as the man is walking 5 feet per second. So once again, don't confuse this problem where we're measuring the speed of the tip of the shadow to the rate of change of the length of the shadow. They're two completely different questions. I hope this video helps explain the differences, and good luck trying some of these on your own.